Hello and welcome to Autumn Math. In this edition of Autumn Math, we're going to talk about inequalities in one variable. We're also going to cover absolute value inequalities. All right, so our objectives today, we want to cover linear inequalities including absolute values. We're going to solve algebraically inequalities including compound inequalities. We want to master the algebraic process, including changing the inequality sign with multiplication division of a negative number. And we want to properly represent solutions of inequalities both graphically and numerically. All right, so just to go back to absolute value, we can think of absolute value as a distance between one place and another. And I can say, let's say I'm facing 7-Eleven. My back is to Starbucks, but they're both the same distance from me. I could think of 7-Eleven as being, well, actually, let's face the other way. I'm going to face Starbucks. And I can think of Starbucks as being a positive direction, let's say half a mile away or 500 meters away. And I can think of 7-Eleven on a number line as being behind me or negative half a mile or 500 meters away from me. When we think about absolute value, we're just thinking about the absolute distance. So both the distance from me into 7-Eleven is the same as the distance from me to Starbucks. So when we consider absolute value, we're just considering the distance from one place to another. We're not considering it as a relation either moving along a number line towards a negative value or a positive value. Okay, so solution of a linear inequality is a value which, when substituted for a variable, makes the statement true. So in this case, I have a linear equation, which has turned into an inequality. 2x plus 7 is less than 3. And when I solve for this, I get x is less than negative 2. So you would solve for this as you would in general for solving for x in this case. X ends up being less than or equal to negative 2. And to solve this on a number line, since negative 2 is not part of the solution, we're going to leave an open circle here and then draw on everything to the left, which is less than negative 2. And again, we'll come back to absolute values in just a moment. All right, so open circle is used to denote either less than or greater than, but not equal to, because the point negative 2 or positive 2, in this case, is not part of the solution. We're going to close that circle to denote less than or equal to and equal to, less than and equal to, or greater than or equal to, when the point, in this case, negative 1, is part of the solution. All right, so the next thing we need to know is that when we're dealing with inequalities, when we multiply or divide by a negative value in order to isolate x, meaning to have a coefficient of a positive 1 in front of x, then we need to change the direction of the inequality sign. So in this case, I start out with my linear inequality. Negative 2x plus 4 is greater than 8. I'm going to divide both sides by negative 2 because I want the coefficient in front of x to be 1, positive 1. When I do that, I divide by negative 2. I need to change the direction of the inequality sign. So I end up with x is less than negative 2. All right, so I want you to take care of these as classwork problems. I'll go through the first one with you, and you can handle the next two. So 7x minus 12 is less than 9. We're going to add 12 to both sides. So we treat it like an equation. X is less than 3. I have an open circle here. I'm going to shade in everything to the left. That's going to be my solution. Okay, you take care of the second two problems. We'll come back in a moment. All right, next two. 15 minus 6x divided by 3 is greater than 3. I'm going to multiply both sides by 3. 15 minus 6x is greater than 9. Now I'm going to add 6x and subtract 9. 6x is less than 6. I personally like to write the variable on the left-hand side. So now 6x is less than 6 looking this way. Divide both sides by 6. X is less than 1. Open circle, shade in everything to the left. Number 3, now I have a multi-step inequality. 8x plus 3 times x plus 1 is greater than 5x minus 9x minus 6. So I'm going to distribute and simplify, combine like terms. And then I'm going to solve the inequality for x. X ends up being greater than 1/5. Open area here for 1/5, shade and everything to the right. Right, so let's talk about, we're going to talk about compound inequalities and absolute value inequalities. Compound inequality consists of two inequalities joined by and or here. And when we think of or, we think of everything that is included in either set. So if we think about two roads that intersect Homestead and Mary, when we say or, it's the union of Homestead or Mary. That means anything on Homestead or anything on Mary is going to be part of the set. So this area here is part of Homestead or Mary. This area here is part of Homestead or Mary. And then, of course, this area that's common to both is part of Homestead or Mary. When we say and, then we think about the intersection, only the area that's common to both. And so the area that we can mark as part of the set of solutions is just going to be what is both on was both on Mary and Homestead. So this value would not be part of the set of the intersection of Homestead and Mary. All right, so compound inequality is, we're going to talk about and then or. So 2x minus 7 is less than or equal to 1. I'm going to solve x is less than or equal to 4. I'm going to graph this here. And then the second, 3x plus 2 is greater than 11. X is greater than 3. And see, I have this and here, so it's only the area that's common to both. So I'm going to graph this here, and my solution is going to be x is greater than 3 and less than or equal to 4. So I have both an algebraic solution and a graphical solution. All right, so when we're writing the inequalities, this is and x is in between 3 and 4. We want to make sure that 3 is the lowest value and 4 is the highest numerical limit. So going from left to right, lowest to highest, and then x is in between. We wouldn't want to write it with the highest value going to the smallest value. This gets you into trouble eventually. Nor do we want to write it this way. X is greater than or equal to x and less than 3. That doesn't, it doesn't make much sense visually. And what we're trying to say is x is in between both 4 and 3 in this case, but this doesn't work out mathematically. Okay, so we're going to move on and we're going to talk about compound inequalities with or. And let me just go back to the example before here. So I wanted to highlight also if this were an inequality, let's just say we had a number line to draw and we wanted to represent x is less than 3 and less than or equal to 4, then what we would end up with, if this were 3 and this were 4, we'd end up with this open circle here and then everything to light. So x is less than 3 and less than or equal to 4. So it's the intersection of the two. We'd end up with just everything to the left of 3. So in a sense, we could eliminate this portion of the inequality. What I wanted to highlight is that this value, this inequality here does not translate to this inequality here. So I just wanted to note the proper representation of an inequality and then tell you what it is not and examples of ways in which you shouldn't write an inequality with opposing inequality symbols where you have the value of x in between the two values. All right, so let's move on again. So compound inequality with or. So it's in either set. We have x is less than or equal to 4, so I'm going to graph that here. The blue line, x is greater than 3, open circle, and to the right. And you can see that as we combine both sets, everything that's in blue or red gives us all real numbers, which is in black. So the algebraic solution would be all real numbers. Graphical solution would be a line that's continuous, the number line. Okay, absolute value inequalities. So absolute value inequalities, I have an absolute value sign, and there are going to be 2 steps when solving this, at least when we approach just the absolute value signs. When we have the absolute value sign, we want to remove the absolute value sign to solve for the inequality just with x and a coefficient. So the first thing we're going to do is we're going to just remove the absolute value brackets, write the inequality as it is, and then we're going to rewrite the second inequality by changing the direction of the sign and changing the sign of the constant here, and then we're going to solve for both. When this value is less than, we'll talk about this in a moment, when this value is less than, it's going to be and then we'll go through another example where it's or. Okay, so less than means and. 4x less than 16, so I'm solving for the left-hand side. X is less than 4. 4x plus 12 is greater than negative 28. 4x is greater than negative 40. X is greater than negative 10. And so I have x is less than 4 and x is greater than negative 10, which I can write this way. And I also want you to solve that graphically, and it'll look like the graphical solution here. X is between negative 10 and 4, not inclusive. Okay, so let's change the direction of the inequality sign. This will end up being an or inequality. You'll see in just a moment. 4x plus 12 is greater than 28. 4x plus 12 is less than negative 28. So same as in the original inequality. And then the second, we're going to change the direction of the inequality sign and the sign of the constant. 4x is greater than 16, x is greater than 4, or x is less than negative 10. All right, so we graph this this way. X is greater than 4, x is less than 10. This would end up being our graphical representation. And then our numeric representation is going to be just x is greater than 4 or x is less than negative 10. Okay, moving on. Some things that you don't want to have the smallest of the largest value here. It's not correct placement, and we want the largest value here. And in this case, x is not less than negative 10. I guess I could say x is not less than negative 10 and greater than 4. And so this value in between the two numeric values, the variable in between the two numeric values, means that we have an and statement. And in this case, x is not or cannot be both greater than negative 4 and less than 10. So it ends up being an or statement. All right. So just again recap, less than 28 or less than the constant means and, greater than means or. All right, so absolute value inequalities, I'm going to have you attempt these, and I'm going to come back and check your work. So I'm going to pause here. All right, so we get 3 plus r is greater than or equal to 11. So remember the two inequalities that we create by removing the absolute value brackets. So the same as in the original, and then we change the direction of the sign, change the sign of the constant. R is greater than or equal to 8, r is less than or equal to, or r is less than or equal to negative 14. And we graph this, or we have the graph representation of the mathematical or algebraic solution. All right, negative 5r is less than 5. Again, the two inequalities. Solve for r is greater than negative 1 and less than 1, and here is the representation. All right, the last part that we want to talk about, you can do this as classwork. I'll show you the answers real quickly. Answer to the second one and answer to the third one. Okay, so multi-step absolute value inequalities. We're going to work from outside in. We're going to isolate the absolute value quantity first, follow the process for removing absolute value brackets, and solve for the variable. All right, so I'm going to subtract 7 from both sides, so I'm working from outside in, then divide by 9. Then I'm going to remove the absolute value brackets, writing my two inequalities, solving for n, and you see here less than means and. I have my algebraic and graphical solution. So I'm going to have you try a couple problems here. I'm going to pause, and then I'm going to show you the answer. Okay, here are the answers. I'm going to work through these quickly. You can pause if you want. And then we have one more to go, compound absolute value inequalities. All right, so I have a compound absolute value inequality. It's greater than 2 and less than negative 5. I'm going to solve the system in pieces for each inequality and then determine the overlap, because this is an and, it's an intersection for each solution. So we're solving here x minus 6 is less or greater than 2. Again, I have my two inequalities, so I'm isolating first the greater than, then the less than. Greater than 8, or x is less than 4. Represent this on a number line graphically, and it's very important for you to do that. And then we're going to come back and resolve the x minus 6 is less than or equal to 5. Again, my two equations, x is less than 11, or x is greater than, and x is greater than negative 1. So this is a less than or equal to. and then I'm going to represent this graphically on the number line, circling in the respective areas, and then I find out what's common to both. So the easiest way in my mind is to solve this graphically first, and then I find the common area for both here to represent this graphically, and then I'm going to write my solution below. X is greater than 1, less than, and less than 4, or X is greater than 8 and less than negative 11. All right, so I'm going to have you solve, this is the one that we just went through, and have you solve one more. You can do this on your own and come back and check your work. And that'll be it for this edition of Odd Math. Okay, so we see that the first inequality gives us the entire number line. Second gives us X is between 9 and 5, so that's the only solution because we need to have every value as part of both sets of solutions. So we represent this algebraically and then graphically. All right, that's it for this edition of Odd Math. Come back and join us next time when we talk about polynomial inequalities.